Looking at example 1 on section 7.3, says consider the region bounded by the y-axis, the x-axis, the graph of this parabolic function, and the line x equals 2. Approximate the region using 4 rectangles, left endpoints, right endpoints, and then midpoints. So 3 different problems here. Okay, so here's a drawing of the function defined between 0 and 2. The output at 2 is 5, 2 squared plus 1 is 5, so that's the output there. Output at 0 is 1, and it's a parabola between those. Alright, so the first part says to do this with left endpoints, approximations. What that means is that we're going to go to the left endpoint of the first subinterval. The subintervals all have width 1/2 because it says to divide it into 4 rectangles, and the right endpoint is 2, so if we're going to divide that up into 4 parts, this is the equal spacing along the x-axis for that. So left endpoints means we're going to go to the left endpoint of the first subinterval, and that's going to be the height of our first rectangle. So we go to that left endpoint, see what the output is there. It's 1. And draw our rectangle with height 1. Okay, and then we'll left endpoint of the second rectangle, draw a rectangle from there, and then a rectangle from the left endpoint of the third subinterval. Will look something like this. And then finally, the fourth subinterval will look something like this. So what we're doing here is approximating the area under this curve with these 4 rectangles. Okay. So to do this, we just have to add up the areas of all of these 4 rectangles. So here's like area 1, 2, 3, and 4. You can see that this is a pretty bad approximation because, we're stopping here at x equals 2. It's supposed to line up there, and all of this is sort of an under approximation of the actual area. So, but the whole point here is we're trying to develop the definite integral out of this. So this is where we start with these approximations. Alright, so that first area, it's a rectangle. All of these have width 1/2, every single one of them. So the first area is its height, which is f of 1, or f of 0, sorry, since it's the left endpoint. F of 0 times the width is 1/2. That's height of the rectangle is the output at 0. The width is 1/2. Second area, we can actually go ahead and label these. This is area 1, area 2, area 3, area 4, and we're just going to add them all up. Okay, so the second area has height, f of the left endpoint of the second subinterval is 1/2, so f of 1/2. Multiply that by the width of the subinterval, which is 1/2 also. Third area is height is f of 1. Width is also 1/2. And finally the fourth area. Plug in the left endpoint of that fourth subinterval. 3/2, so that's going to be, the height of it is f of 3/2, and its width is also 1/2. Okay, so now we just have to figure out what are these values. What is f of 0, what is f of 1/2, etc. So f of 0, that's the output we got at 0. So remember what this function is. It's f of x equals x squared plus 1. So if we plug in 0 there, the left endpoint, we get 1. This is 1 times 1/2. So that's 1/2. F of 1/2, that's the left endpoint of the second subinterval. We get that by plugging that into the function. So 1/2 squared. 1/2 squared is 1/4 plus 1 is 5/4. And multiply that by the half. So you get 5/8 for that. Okay. Third one, f of 1. Plug 1 into that function, you get 1 squared plus 1, it's 2. And multiply that by 1/2. Output there is 1. Last one, f of 3/2. Plug in 3/2 to the function, that gives us the height of the rectangle. The width is 1/2, so how do we find the height? Plug it into the function. 3/2 squared is 9/4. 9/4 plus 1, 13/4. So 13/4 times 1/2 gives us 13/8. And so the approximate area of these things is the sum from A1 to A4. We can use summation notation for that. It's going to give us something that looks like this. I equals 1 to 4, A sub I, and that just means we're just going to add them all together. So start with index 1, it uses A1, iterate to 2, plus 2, or plus A2, to 3, A3, to 4, A4, and we stop at 4 since that's where the top is. Okay, so A1 was 1/2, A2, 5/8, A3, 1, A4, 13/8. And so that gives us 15 over 4. And you can write that as a decimal as 3.75. So this would be a left endpoint approximation for the area under the curve. Again, this is an under approximation because we're missing all that area right there. We'll do the right endpoint next, and then we'll do the midpoint last. And we'll compare the three answers and see what the best one of them is. Alright, so for the next one, we're going to use right endpoints. So for the right endpoint approximation, we go to the right end of the first subinterval, and that's going to determine the height of our first rectangle. So we'll put a dot there, and since we're on the first subinterval, we have to stay there, so we're actually going to go left for our first rectangle. First rectangle will look something like that. Fix that a little bit. So something like this, and then second rectangle will go to the right endpoint of the next subinterval to go back to the left to figure out what that rectangle is going to look like. So there's our second one. Third one, we go to the right endpoint of the third subinterval. Third rectangle is going to look something like this. And the fourth one, right endpoint of the fourth subinterval. And these are all supposed to look the same width. Hard to do that in my drawing here, but anyway, they all do have width 1/2. You can see that this is clearly going to be an over approximation of the area. Once we add these all up, we'll have all this extra area here. Okay, so this is going to be super similar to the last one. In fact, I'm going to do it a little bit faster. Now, the first area is going to be bigger. This is area 1, and so on. So for that one, same idea. Now we just have a different height. That first height is now f of 1/2 times the width, again 1/2. So we already saw that f of 1/2, we squared that 1/4 plus 1, that was 5/4. We multiply that by 1/2, we got 5/8. The second area now is going to be f of 1 times 1/2. And we saw already, we plug in 1 there, we got 2 out. And multiply that by 1/2, we get 1. My scale is not very good too, that should be 2 for the output there. Anyway, for A3, now its height is determined by this right subinterval now, or the right endpoint of this subinterval. So that was 9/4 plus 1, that was 13 over 4. I'm just going to go ahead and write that, 13/4. And then finally for our last one, now this is going to be determined by the right endpoint of the last subinterval. Height here is 2 squared, 4 plus 1 is 5, so that's going to be 5. Multiply that by the width of the subinterval, 1/2. So that's going to be 5/2. Okay, so same idea. We're just going to add all these up. I'm going to just abbreviate this now. The total area, and we might call this an upper approximation. So the total area is going to be the sum from I equal 1 to 4 of the a sub i's. And now the sum is going to be a little bit different now, obviously, because the first number is different and the last number is different. So you can kind of see what we did here. compared to the last one, it's sort of shifted everything over one. So now it's 5/8 plus 1 plus 13/4 plus 5/2. And that is 59/8, or 7.375. Okay, so comparing that to our last one of 3.75, this is clearly much bigger. So this is an over approximation. We'll call that the upper approximation. Lastly, we'll do the midpoints. And the midpoint approximation is a little bit harder to do because you have to go to the midpoint of each subinterval. It means you have to figure out what the midpoint of each one of them is, first of all. So halfway between 0 and 1/2 is 1/4. So that's that one. Midpoint here, it's going to be 3/4. And midpoint here, see, halfway between 1 and 1.5, that's 1.25. So that's 5/4. And those are supposed to be 4s. I don't know why this thing is doing this. Anyway, that's 5/4. This is going to be 7/4. And then what we're going to do on our function, draw the function again, we're going to base each rectangle, the height of each rectangle, on that midpoint of each subinterval. Okay, so that first one's going to be somewhere there. This one, we'll put a dot right there. And our rectangle is going to look something like this here. And my drawing is not great, but you can hopefully see kind of what's happening here. Okay, so it's going to look something like that. Now these ones, you can tell, are actually going to be a much better approximation, because this is a little bit of an under approximation, or over actually right there, and this is a little bit under. They kind of have the effect of canceling each other out. Not exactly. You can kind of see that this area here is a little bit greater of an under approximation than we've got to sort of fix over here for the over approximation. Anyway, the idea here is we're just going to plug in all those midpoints. So we get f of 1/4 times 1/2. That's the area 1. I'm just going to go ahead and write all of them. Then f of, the next one was 3/4 times 1/2. And then the next one, f of 5/4 times 1/2. And then the last one, f of 7/4. And multiply that by 1/2 as well. And then if you plug all these in, I'm just going to sort of skip through this. We saw how we got these numbers. We're plugging them right back into here. So f of 1/4, 1/4 squared plus 1, and 3/4 and 5/4 and 7/4, etc. So if you do all that, you get 17/16 times 1/2. F of 3/4 is 25/16 times 1/2. And 41/16 half, and 65/16 65/16 and a half there. Okay, so multiplying all these by 1/2 and adding everything up, you get 37/8, or as a decimal, 4.625. 4.625. Okay, now if you compare that to the other answers that we got, what did we get? 3.75 and 7.375. This one is right between them, so this one is actually a better approximation than the other two, as we had already seen. So that's one way that you can get a pretty good approximation. You can use the midpoint. Another way to get a better approximation is actually just to take the average of the right and the left endpoint approximations, and that gives a pretty good approximation as well. So as we'll see in this section, though, we can actually do much better than these approximations. We can actually get the exact area under the curve with what's called the definite integral.